the previous lecture, I gave motivation for the study of wetting on rough and textured surfaces. I gave several examples from natural as well as industrial or technological settings where rough surfaces naturally are present, and therefore it's important to understand the relationship between the contact angle that you see, the apparent contact angle that you see, and the microscopic angle, that's the Young's angle, or the equilibrium angle, the Young's angle, and the various surface energies that are present in the system. And more importantly, the relationship between the apparent angle and the roughness parameters. I then extended the discussion to look at wetting on an ideal rough surface. This is a surface which is atomically smooth, chemically homogeneous, and which means that the surface energy of the solid does not change in space. Now, this was a discussion that we had already. This was a problem that we've already studied in the two-dimensional settings. I just redid the problem for an axisymmetric case, and the analysis is identical, except that we get the integrations are slightly different because um, the area element that we've taken is slightly different. We have not included gravity per se, but instead we have put an arbitrary external field, and we notice that irrespective of these differences, the result finally is the same as far as the contact angle boundary condition is concerned. The contact angle condition that emerges from this is again the Young's angle. We also obtain the Young's angle by taking a slightly different approach, which is just taking an interface and moving it by a small amount x dx and asking what is the work done for this movement, and we just incorporated we have to only consider the changes in the energy that result because of moving the contact line. Either the movement could be to the left or right, that does not really matter. And when we set the this quantity dw to 0, then again the Young's law emerges. This is all valid for a smooth surface where the surface energy is the same, and theta y is the Young's angle. Now I want to also emphasize this one box that I've highlighted. This is the dependence of this energy functional on several quantities such as the slope, the height of the position of the contact, the interface, the surface energies, and of course the external field that we have here. We will be using this kind of a relationship in this expression when we do rough surfaces. Now, in the case of rough surfaces, I introduced three kinds of rough surfaces, and that's exactly where we are going to start today's lecture. So let's consider the first rough surface. You can see an undulating zigzag pattern. The liquid penetrates into the crevices that you see in the undulation, meaning the solid is completely wet in this case, and this is referred to as the Wenzel state. So in this state, the liquid penetrates the undulations on the surface and wets it. Okay, that's the first point. And second thing is outside the contact line, outside the triple line or the contact line, triple line, that's the contact line around the boundary, the surface is dry. This was observed by Wenzel. I believe it was done in Wenzel in 1936. He proposed a model for this state. Then we have the Cassie-Baxter state. And in the Cassie-Baxter state, the droplet, there are two kinds of Cassie-Baxters that I'm highlighting here. The first one is where there is chemical heterogeneity. There's chemical heterogeneity. So each of these little squares that I'm showing, these are of different surface energies. Now we will do the analysis for a surface um smooth. And finally, we have another Cassie-Baxter state, which is droplet is, or I should just say, air pockets are trapped between the surface undulations or surface roughness elements. So, in other words, these little regions that you see here, all these regions, these are air pockets. Now, we want to do an analysis for each of these cases, but before we do this, let me first define how do we characterize roughness. Okay, so we'll define two roughness parameters. The first one, we'll just call it as R, and this quantity R is the total surface area of the rough surface to the projected surface area. And this quantity is always greater than or equal to 1. For a perfectly smooth flat surface, this quantity is exactly equal to 1. But for any rough surface, the undulations will increase the surface area, and therefore the roughness parameter R is greater than 1. We have another parameter which we'll call it as phi s, and this phi s is primarily valid in the last case, the Cassie-Baxter state with air pockets. This is the area of the islands to the projected area. So I'm really referring to these islands here. This is an island. I hope you can see this. I'm highlighting them with green. These are the little islands where the drop is basically is making contact with the solid. In all the other places, it is supported on an air pocket, right? And clearly this quantity has to be less than 1. Now, if this quantity is exactly equal to 1, then you have a smooth surface, right? Now, having defined both these parameters, let us now look at the analysis first for the Wenzel model. I call it the Wenzel model. This is because this is a model that Wenzel originally proposed, I think, in 1936. So the idea goes back to first writing the idea is exactly similar to what we've done for a smooth surface. But let's look at the different parts of this box, the highlighted box that I've put here. This is basically the integrand of this energy functional. Now there are several terms here. The first term that I'm just highlighting now, this comes from this is the contribution from the surface of the liquid and the gas above, right? And that's why you have the surface tension gamma. Sorry about that. Now if you look at the next one here, if you integrate this quantity, then you basically cover the surface area. This is the surface area of the droplet or the projected area of the droplet on the solid surface. This is the wetting area of the droplet on the solid surface. and this is the change in the energy because of that wetting. So this quantity essentially now is different when you look at a rough surface, because in the rough surface what you really have is this area of the solid surface on which the droplet has wet has changed. So let's now look at the Wenzel model. In the Wenzel model, the droplet is touching the surface everywhere. Okay, so if we write down the um, energy functional, which is going to be a function of h, x, h and hx, this quantity is just going from 0 to a 2 pi gamma x 1 plus hx square. This part has not changed. This is from the surface of the droplet, consideration from the surface of the droplet. But the moment I basically look at this contribution from the surface, then I have 2 pi x times r. This extra r tells me the increase in the surface area. Recall what is the definition of r. Definition of r is total surface area to the projected surface area. Projected surface area is what you would have for us if this surface was absolutely smooth in the Wenzel model. But the total surface area is nothing but r times the equivalent flat surface area or the projected surface area. So the total surface area is just a multiplication of the flat surface area with r. That's exactly what I have done now. I've just multiplied by r, and then the rest of it remains the same. And the body force, the gravity term, external field does not really change, so that remains the same. So we can now do an analysis exactly on this quantity. So R increases the wetted surface area due to roughness. Okay, the parameter R, and obviously R is greater than 1. Right. There is no other change. And if we continue this analysis, what we find is we can again impose the same volume constraint. The volume constraint would be 0 to a 2 pi x h dx is constant, and we now have j, which is a function of x, h and hx, is simply going to be an integral of this quantity 0 to a f. Let's call it slightly different. Let's put a subscript w to state that this energy functional is for the Wenzel state. I have fw of x, h and hx dx, and this quantity f is this fw of h and hx. We'll follow the same analysis that we have here. The boundary term essentially gives me fw minus hx times del fw by del hx evaluated at x equal to a 0. Note that the droplet is still making it's roughly from the top view it looks like a circle of radius a. If we apply this, the only difference that we now get is this extra r term that we have to carry forward. But let me quickly do this. I have 1 plus hx square. Now I have r times gamma sl minus gamma s minus gamma hx square by square root of 1 plus hx square evaluated at x equal to a. Note that I'm not doing this derivation again in detail. I'm not taking the derivatives and substituting into this boundary condition again because this is very similar to what we had done in a couple of earlier lectures, and therefore I simply have, if I simplify this, I simply get let me write it slightly differently. We have 1 by 1 plus hx square evaluated at x equal to a, this essentially becomes r times gamma s, gamma SL divided by gamma, right? Now, the first quantity that you see here is clearly the second quantity that you see here, sorry, this is clearly the Young's angle. This is a cosine of the Young's angle, theta y, and this quantity essentially becomes cosine of a theta star. Why is it a theta star? Because if you locally look at the angle, you have this rough surface here, and you have a droplet that is making an angle of theta star. So if you look at a small triangle again, this is dh and this is dx and theta star, then we have 1 by square root of 1 plus hx square evaluated at this point x equal to a is cosine of this angle theta star. Okay, and therefore what I now have is cosine of theta star is r times of cosine of theta y. This is the Wenzel model. The Wenzel model simply says, give me a rough surface of a roughness parameter r, and if the droplet is fully penetrating into the surface, if the liquid is penetrating into the surface and completely wetting the surface, then the cosine of the angle is simply r times cosine of the Young's angle, what the equivalent one for a smooth surface. Okay, so once you know a smooth surface, an atomically smooth surface, then you can, if the Wenz model is valid, then you can straight away determine the angle for a rough surface. Okay, now there are a couple of other predictions that come out of the Young's model. We will look at that in a bit. I want to look at the heterogeneous case as well, the chemically heterogeneous surface as well. But let me look at some observations. This is observations, I should say, this is observations from the Wenzel model. The first observation is inherently smooth hydrophilic surfaces. Hydrophilic surfaces. These are hydrophilic, these are, I should mention, inherently smooth. Inherently smooth hydrophilic surfaces, meaning the Young's angle is less than 90 degrees, right, will become more hydrophilic when made rough, right? This is due to the fact that theta star becomes less than theta y since r is greater than 1. So if you look at the cosine function, when angle is 0, it's at 1, and then it's a decreasing function. So if your cosine of the theta star is larger than the cosine of theta y, that's the equilibrium angle, then the only way that can happen is when theta star is less than theta y. Okay, we will just make a quick sketch of this. This is the cosine function, and this quantity is pi by 2. So if you're in the hydrophilic regime, this is hydrophilic for these angles. We are talking about this theta versus cosine of theta. What I'm essentially describing is a case where if your Young's angle is this, that is theta y, then you need to have a value of cosine of theta star, which is larger than theta y. So it means that you essentially move up this curve, and therefore your effective roughness, effective apparent contact angle is even less than the Young's angle. So theta star here, I should highlight, is also referred to as the apparent contact angle. This is the angle that typically one sees in an experiment. Okay. I'm not going to go into philosophical issues. I'm using the words carefully here. Philosophical issues, whether this is really the angle that we see on the rough surface, exactly very microscopically when we zoom in. This is the angle that we normally see in an experiment. Okay. So the same reason we can also extend it to the other case. Inherently smooth hydrophobic surfaces, that is theta y greater than pi by 2, become more hydrophobic. Okay. Now, it's also important to understand that this analysis that we have also done is independent of any external field. That's again one of the beauties of this simple model. The external field that we have applied, whether be it the gravitational field as an example, it does not basically alter the wetting property very close to the contact line, very close to the surface, and therefore cosine of theta star essentially is only a roughness dependent parameter. The theta star is a roughness determined quantity, right? So we can also look at the Young's model from a very simple thermodynamic setting. Let's also look at that very quickly. A simple thermodynamic I should say grounding for the Wenzel model. So essentially, if you look at the specific surface energies, then we can essentially say the cosine of the theta star can be related to the specific surface energy. So in other words, the apparent contact angle in a Wenzel-like wetting state can be written as follows. This will be, let's say, some G S, let's call it a star, minus G S L divided by gamma. So what are these quantities here? G and GSL, these are specific surface energies at the solid air and solid liquid interfaces. Now notice that if this was a smooth surface, then the specific surface energy is nothing but surface energy per unit area. These are just nothing but the surface tensions of the solid and the solid liquid interface. This theta star essentially becomes the Young's angle, correct? Now, because we have undulations on the surface, the only thing that changes is the surface roughness changes the area, and the area effectively changes the total surface energy, right? So the specific surface energies these quantities, specific surface energies for a rough surface. Now we can also define two new quantities. These are GS. We can also define two quantities, that is GS and GSL. These are specific surface energies for a smooth surface. Therefore, I can straight away conclude that the specific surface energy for a rough surface will simply be the roughness parameter R times GS, because essentially the effective area has increased and therefore the effective specific surface energy has changed. And similarly, this quantity is just R times GSL, and from this I simply get cosine of theta star is nothing but R times GS minus GSL by gamma, right? Now, we already know that Gs is simply the surface energy of the solid. We'll just call it as gamma S. And this GSL is nothing but the specific surface energy of the solid liquid interface. That's just gamma SL. And therefore, I simply have R times gamma S minus gamma SL by gamma. Okay, and therefore cosine of theta star is nothing but R times cosine of theta y. This is again uh, the same thermodynamic reason that the effective surface area has increased, and therefore the Wenzel model essentially gives me a different contact angle. Either we can arrive at this result either through the energy minimization approach or through the simple thermodynamic explanation. Now let's look at the next model. This is the Cassie-Baxter state. Model for a chemically heterogeneous surface. So to understand this, we have to understand that the surface is basically having different roughness different surface energies on this checkered board pattern. So each of these checkered board pattern areas that I'm showing here, they have different surface energies. Implies gamma S, let's call it as gamma Si, and gamma SL. These are surface energies of solid and solid liquid regions for different different surface regions. So we have different surface regions. The surface regions are roughly modeled in this checkerboard pattern, but it is not necessarily a checkerboard pattern. It could be any other pattern, and each of these surfaces have different surface energies. So there are basically two surface energies that we have to deal with. One is the surface energy of the solid itself. This is nothing but the solid air surface energy, and the other one is the surface energy of the liquid. So the superscript I, this I indicates a count over all the different regions. So I could have the droplet being described by n such regions on the surface, and the idea is that to get the total surface energy, we have to sum over all these regions, but taking into account that these different regions have different the different surface energies. So what's the idea here? The idea is that the energy functional Again, we have the same thing here, J, which is a function of H, X, H, and HX. This quantity will integrate from 0 to A, where you have a droplet here whose radial extent is A on the surface. This is a smooth solid surface. I should emphasize that we are talking about a chemically heterogeneous smooth surface. Okay, so we will not take undulations into account. At this point, we have 2 pi gamma x 1 plus hx square. This is the contribution from the droplet air interface. Okay, so this does not change. Now we have to integrate over the entire uh, region where the droplet is making contact with the surface. Okay, that's the region, the wetted region on the solid surface. So this will be 2 pi x. But now, if I have n number of checkerboard patterns, then I'll have to sum from 1 to n. I have so if I have each of these regions, let's say in each such square, if I have a small contribution from of two different surfaces in each square, then essentially I have solid, liquid, so this quantity F phi s here is like what we had talked about islands here. This is like of the area fractions of different types of surfaces. So let's say I have, and by the way, this has to have a superscript as well. So we'll call this a superscript of I. So let's say if I have over this entire surface of the droplet, maybe I should highlight this. If I look at the entire surface area of this surface here at the bottom, this surface basically is divided into n checkerboard patterns, of which I have different contributions of type 1. So the I becomes 1. Then I have type 2 of the surface, I is 2, and so on, up to all the way up to, there are, let's say, n types of such surfaces. So each of these surfaces, that's the area fraction. So that's why we are I've used the same parameter phi s. Phi s we had defined earlier as the area of the islands for a pillared like structure to the projected area. This is like area of these little islands. There are little islands or pockets of surfaces of different chemical properties, and the chemical properties are primarily influence the surface energies. Now we can basically take this expression, impose a volume constraint. I simply have J of x, h, hx essentially becomes, or rather I should say f, this quantity f essentially becomes 2 pi gamma x into square root of 1 plus hx square plus 2 pi x, summation goes from I1 to n, phi s of I. For each I, there is a difference in the surface energies. This is, I'll just call it as gamma s plus u of x comma h. Now we have a Lagrange multiplier lambda times 2 pi hx. Therefore, the energy functional which has to be minimized is simply going to be from 0 to a f of hx dx, right? So this is the minimization problem. And if we do the analysis like before, the same procedure as carried out for the Wenzel model, that we get cosine of theta star will simply be summation of I going from 1 to n phi s of I times gamma I of s minus gamma I of SL divided by gamma. This model is Cassie-Baxter model for a chemically heterogeneous smooth surface. This is the general model where I have n such surface elements. Let's consider a special case. If the surface or the substrate, the solid substrate, consists of just two kinds of chemical heterogeneities, then we get cosine of theta star will simply be f1 cosine of theta 1 plus f2 cosine of theta 2, right? Now, what is theta 1 and theta 2? Or theta 1 and theta 2 are the local Young's angles for each such smooth surface with corresponding chemical heterogeneity or corresponding chemical properties. Let me explain what I mean by this. So if we have just two kinds of heterogeneities that are present on the surface, and essentially the summation in the above model just goes from 1 to 2, and all I have to do now is to sum it over both those kinds of surface. So for example, I could make a surface which is partly coated with I could do, let's say, silanization, which basically where you change the local contact angle, but I do the silanization on the surface in some kind of a checkered pattern, or selectively I do it on certain parts of the surface. This can be done these days using masking techniques. Then what you actually do is you have only two kinds of surfaces. Now basically you have a surface where the contact angle is, let's say, local contact angle is theta 1 and local contact angle is theta 2. This theta 1 and theta 2 would be the Young's angle that you would get if the entire surface was of only one heterogeneity, one surface chemical property. So for example, if you have an untreated glass plate on a surface, then the angle, let's say, is theta 2, and now you do some chemical treatment on the glass surface, then the angle is theta 1, Now you can have a combination where portions of the glass plate are treated and portions of the glass plate are not treated. Now what you now have is a composite glass surface where parts of it are treated and parts of it are untreated. Once you have a droplet that is sitting on a surface, you need to know how much of portion of the glass plate, how much of the portion of the droplet is covering the treated and the untreated portions. That's basically represented by F1 and F2. These are like area fractions. The area, select area of these islands of different heterogeneities, different chemical compositions, and once you know that, you can calculate the effective angle that you would see. That's the Wenzel, this is the Cassie-Baxter model. Okay. Now, keeping the time in mind, I will look at the other case, which is the Cassie-Baxter case, where we have a tiny air pockets in the next lecture. Now, another thing that we also may be interested in knowing is, are there simple criteria that we can come up to find out what happens when can the droplet go from one case to another case? This can happen for a variety of reasons. One way you can actually promote a different kind of wetting is, let's say you take a Cassie-Baxter state with tiny air pockets, you could actually shake the droplet. You could continuously shake the droplet and you could actually effectively change the wetting nature. We'll look at the Cassie-Baxter model where we have tiny air pockets between the roughness elements, and then we will look at some simple transition criteria, and it's not exhaustive by any means. So I'll see you around in the next lecture. Thank you.